Welcome to the Financial Modeling Teacher. In this presentation, we simulate an asset price using the lognormal model. We cover the following contents: the lognormal model itself, then we discuss the growth rates and their distributions. Then that leads us to introducing the stochastic differential equation, which is the model that captures the evolution of the stock price itself or the asset price, as well as a discretized version. Then we follow a few steps in a way of a spreadsheet modeling to demonstrate a simulation process for few parts. Then this now leads us to the final product of a terminal asset price. Then the last discussion will then be the lognormal distribution of the asset returns as T. Now the lognormal model itself, we first define it as ST equal to SO, then E to the power XT. In other words, we are saying the asset price at time T will be equal to, or it's made up of, the initial price SO by the exponent of the rate itself. So where XT, the rate, is a continuously compounded rate which moves the price from the initial price SO to the price we require at time T, ST. The ST is the future asset price at time T, but T must be greater or equal to 0. As we've seen, the SO is a today's price or the current price, and then S with a big letter T will be the terminal asset price. An extract from an Excel spreadsheet where we had data by way of an index, which we don't necessarily have to name the name, but it's an index from which we extracted this return data. Then we use the adjusted close as our level of the index or the ST itself. So that now to calculate the return here, the log return, we are saying PT, which is a ratio of the current to the previous price, and we work out the logarithm thereof. We specifically denote XT here as RT, not necessarily RT, but XT itself, as a random variable XT, which we will define to be normally distributed. This leads us to this slide here where we have XT model as a normal distribution, and on the right side we have a histogram as well as a probability density plot of such XT, which is just a series of log returns that we've studied before. But then what is the purpose here? The purpose is so that we can predict ST. We further assume the normal distribution despite those stylized facts and the non-normality assumptions. We simply view that in order to simplify our financial model, we still want to make mention of the normal distribution. This then leads us to being able to estimate these parameters mu and t, with mu now being mu at time t, as well as sigma squared t being the variance at time t, where now xt is normally distributed with these two parameters. But given the infinite nature of these parameters, t, the big T might be several years or so, but then it is always best to annualize these parameters. Of course, we will be guided by the time period we are discussing. For instance, in this case, we are saying our T is just 1. So then it means now our parameters u, mu t and sigma t will simply be, let's say, mu1 for year t1 multiplied by t itself, and then the sigma t squared will now be that sigma multiplied by t itself. Now the other thing is that now the mu can actually be adjusted by introducing this half sigma squared. Without really dwelling much into that, there are some future discussions that we'll explore in other videos where we have a full detail of this. But for now, we will just use and apply this adjustment in our models. There will be something called Ito's lemma that we'll discuss among others. And many other texts do derive how this mu1 minus half t comes into the whole picture. This now leads us to the introduction of the stochastic differential equation, where we have the value of the asset st as a log-normally distributed variable, random variable, but its return r, which is st over st minus 1 into log, it's normally distributed. So we have the asset as log normal, whereas the return is normal. Now the asset price st evolves according to this stochastic differential equation, dst equal to r st dt plus sigma st dw. The first part, or the first term, r sdt, is a deterministic part, meaning that it is constant, whereas the other part is stochastic, in a sense that introduction of this Brownian motion gives it that random element. Now when we divide this equation 1 with st, both right and left side will end up with just r dt plus sigma dw. Now we further adjust the r with that half sigma squared. So that now the next step will now be a discretized version of that SDE2. The reason for discretization is because then data being measured at fixed points, it is then easy for us to work with such data, more especially when we do a simulation. So now the dt here, which is a time step or a fixed interval, plays an important role here of being able to assign or apportion time into this time differential into this discrete version of the equation. There are a couple of practices, especially in simulation, where this discretization is applied. Remember, in principle or in basic statistics, we introduced the continuous this random variable versus a discrete random variable, meaning that the discrete one can be measured at a point, whereas the continuous random variable is continuous. But for ease of computation and calculation, there's always a practice to discretize the continuous time equation that we had in equation 1 and 2 into discrete one. The popular model is something called the Euler discretizing or the Euler Maruyama and others. So the small wt here, whereas that was a Brownian motion with a big W, we now have small wt, purposely just to emphasize or denote it in this fashion in order to introduce the standard normal variable with a mean 0 and a variance of 1. So this will now have an effect of adding a random nature or variation in this equation. So we now apply that equation in order to perform our simulation. So we let the estimate mu hat. We all know the practice of denoting an estimated parameters with a hat. So we have a hat. We have already calculated a mu as the mean of those returns xt. But we further saying we want to annualize it, and we multiply it by 252 in order for it to be annual. Then the same applies with a sigma, an estimated standard deviation or a volatility. It will now be a sigma hat equal to sigma multiplied by square root of 252. Then we have a delta t equal to 1 over 252 because we are talking about a daily data here. As a result, we divide it by 252 being a daily data. Then we have an initial level, SO. This SO will be looking at our data of, let's say, the past 10, 15 years. The SO will be the most recent closing price in our data. So that now this same equation that we had will now be translated into the Excel version as highlighted in blue. So in our simulation, the first thing that we shall do is we have in those cells, we name variables est underscore mu is equal to h3 by 252. And the sigma is est sigma shall be I3 multiplied by the square root of 252. And then delta t will be 1 minus 100. In this case, we're just using 100 days, so we've had our time step just reduced to 100. And then we have SOS F2337. That would be the last entry under the close column will give us that. So now in our model, to avoid using dollar signs, we would just label and create names for this range of cells as we will be applying them from time to time in our model. So we go into formula, from the Excel ribbon we'll go formula, and then under formula there it'll say create names. We have highlighted firstly the all the cells mu, est mu up to SO, as well as the columns with equations up to where it says F2337. Then we say create name, and then we check left column, and then we type OK. Look at the bottom what we have selected exactly, and then we type OK in our spreadsheet. So it will be nice for you guys just to go through the accompany as worksheet in order to perform an exercise and as well as an example of this worksheet. So now the first thing, now having populated the initial entry with this details, that is cell S2, we will drag this formula to cell FN2, in other words, just the first row. Because then in the next row, we're going to take the values that we obtained in the first row to determine the next exponentiation, the next compounding. So now we move to cell S3. We can copy everything from row 1, but then in cell S2, we change just the SO part to become S2. And from there, we can now drag it across as our second row. In other words, we drag it to FN3. So now the first row now determines the second row, in a sense that the first row was based on the last entry F2337, which is the initial SO in our model, the initial estimated asset price from which we want to simulate. Then dragging, highlighting S3 to Fn, and then we can replicate the whole row into the following cells S4 up to F103 at the bottom. Then after the simulation, we do a plot of few paths. Remember our simulation, we've replicated and populated into about 152 paths. So it will be about 152 columns to the right and only about 100 raised to the bottom so that we can easily work. In a way, a program like Python or even Julia or MATLAB can perform this quite nicely. But unfortunately, the spreadsheets being what we have as a closest tools, we can do a lot with it as well, except that the tediousness of having to replicate right across the spreadsheet. But at the end, this is a nice picture that we have. We can say the initial price was just around 6,000. And with a compounding as well as the random nature, we will have numbers of figures going up to just over 8,000 or even below up to 5,000. Remember, this being a random variation or random process, we will have the movements of the stock price going either up or down. But it does behave well because in a way it does still give us somehow a confidence level that makes us comfortable that our simulation can be right. That's the last thing here, and the final step of our simulation. We have terminal values denoted with S with the big letter T. In our simulation spreadsheet, they are taken from row 103. That is the last line of these 152 paths. To the far right of our worksheet of this slide, we have an extract from the Excel spreadsheet where we computed the mean, the standard deviation, the minimum price, the maximum price based on that row, the skewness, the kurtosis, and a total number of about 24 observations. We assume that at the level 95% level, the upper value could be about 6910, while the lower is about 6582. We've seen also with our simulation plot that the average is definitely around 6,000. So to work out the confidence interval, we have a 95% level of confidence denoted by alpha, so that the confidence interval is simply mu plus or minus, and then 1 minus alpha, which is now our critical z or a t statistic or value, then by the standard error, which is computed as sigma divided by the square root of n. So this now leads us to having to plot, demonstrate that these 103 terminal values could be plotted as a log normal distribution. As we can see, supposing this is a terminal price per up after 100 at the 100th day of our simulation, we see from this distribution plot that the minimum is slightly below 5,000, whereas the positive goes up beyond 9,000, and immediately you can see there's a positive skew as against negative, and this distribution is positive starting above 0, and that positive skew definitely making it look very much log normal as against normal. The blue is the actual observed ST, whereas magenta line is for a PDF, which is a calculation of a probability density function according to a program. Now, this concludes our presentation, and for the accompanied spreadsheet, please follow the link lognormal on our YouTube channel and use the password 2024 to open the worksheet. Thank you for listening. I hope you enjoyed the presentation. I am the financial modeling teacher. Thank you.